So last week we talked about structure of the nervous system, right? But I would like to clarify what kind of structure we talked about. And that was what we would call fine structure. Okay? We might think about that as microscopic, right? We talked about ion channels, we talked about dendrites, we talked about axons, things that you need, Carolina, a microscope to see, right? Okay? We're not talking about big groups of cells, we're not talking about nuclei, we're not talking about, the bumps and ridges and things on your cortex, we're talking about other things, right? Cellular and subcellular components. So that's what we talked about. We still need to talk about some structure of the nervous system, but we're going to talk about it in a broader sense, right? We're going to talk about collections of brain regions and circuits and what some of these places do. Now we're going to go through this fairly quickly. I will tell you what's important for now, Rosie, and then I will tell you what you're going to learn later, and you can just wait on it, right? So don't try to learn all of this at once because we're going to go through it kind of quickly, and then we'll jump into Chapter 4, which is a little more intense and connects back to Chapter 2. We talked about basic features. We'll briefly talk about development, where we think that's important, and then cover some major systems in the brain and nervous system. Some of you have taken like a basic biology course. Some of you have taken an anatomy course. You went over this sort of list of words in detail. I'm not going to, we'll use these words as we need to. If you're not familiar with it, spend a little time with it, right? If you are familiar with it, just move on and you're ready to roll. I'm not going to ask you questions like which nucleus is anterior to some other nucleus, right? That seems ridiculous unless it's like an anatomy course. But many places in your brain are going to carry these sort of names, and it might be helpful so that you understand where you sort of are, right, Jared? So you just have some idea of location, okay? Occasionally, you get an urge to cut a brain. It just happens, right, Adriana? I'm not going to ask you when, but it just happens. I would usually ask first before you do this, right? Don't just like start cutting people's brains without asking. Why would we cut a brain? Well, it's really hard to fit in a box if you don't, right? So it needs to be in pieces. The other reason is it helps you visualize what's on the inside, right? If you want to look at brain structures, you might want to slice inside, right? Because most of what's going on is going to be going on inside your brain. It's not like fun stuff on the surface, right? Although the surface is kind of interesting and important. There are different ways we might cut this. You might hear about a cross-section or a frontal section. We'll refer to that typically as coronal, horizontal, and then sagittal, mid-sagittal, parasagittal. Those guys are all kind of going down the middle. Hey, we covered this last week. There's just a little review for you. We can skip through that. All right, here's that brain. We're blocking it. We're cutting it in these planes. Right, here you go. This is a coronal section, so you're kind of looking at it, the front of it. This is a sagittal section. You've sliced it in the middle. And this is a horizontal section, so we've just kind of chopped the top off somebody's head, right? So that's exciting. If you notice, the brain looks completely different in all three of those views, right? And that's kind of important. You can see different structures in different ways. So this guy right here is called the corpus callosum. Very important for connecting the left hemisphere to the right hemisphere, right? So it keeps you from walking in circles. If you have intractable epilepsy, they will occasionally come in and cut this guy, right? So they'll split it. We talked a little bit about that before. So they'll split that. So your left and right hemispheres are not communicating with each other. So that's the corpus callosum there in a sagittal view. This is the corpus callosum in a coronal view. All right? And, well, here's part of the corpus callosum in this particular horizontal view. And it would sort of come up and over an arch like this, as we see here. You can see that it has three completely different shapes. You have to think about this three-dimensional structure, right? Your brain is a three-dimensional structure. The things inside of it are a three-dimensional structure. Depending on how we want to look at it, we're going to cut the brain in different ways. By the way, this is your spinal cord down here. Most of you are not alligators. I know a couple of you are, but that's okay. We'll fix that. Why is it important to realize you're not an alligator? We want to think about this thing called the neuraxis, right? And this guy's a quadruped. And this guy's a biped. Okay. A lot of the experiments that we talk about, a lot of the information that we have are going to be from quadrupeds, not alligators. Alligator brains are not terribly interesting. They don't have a whole lot going on, right? They've got the part that makes them bite and the part that makes them swim, and that's about it. But the other quadruped that we might spend a lot of time thinking about are rats. Right? We'll talk a lot about rat studies, other rodent studies, so that's kind of important to think about. Think about the orientation of your head in relationship to your spinal cord. Okay, if you think about the way the brain goes in a human, that makes some change on words like anterior, posterior, ventral, dorsal, things like that, right? If we talk about a dorsal fin on a shark, we think about that there. If you put a dorsal fin on a human, it goes that way, right? In case anybody wanted an add-on. I don't know, Jordan. Some people like dorsal fins, right? I can see that's the next phase of implants, or dorsal fins. I'm going to try to start that. You have to start with a small dorsal fin first and then stretch the skin over time. So it's a process. You don't want to go straight for the great white the first time, right? You got to kind of start with a smaller one. And this woman, I don't know. She's got like a neck cramp or something. I'm not sure what's going on with her shoulders there. She's got them up by her ears. It doesn't really make a difference with the medial lateral business, but dorsal's at the top, kind of here and back here. All right, meninges. These guys are fun. These are protective sheaths around your brain and your spinal cord, so it's going to be central nervous system only, right? You've got 3 layers of your meninges. The first is the dura mater, which means tough mother. Right? It's kind of a fun name. Anybody ever, so this is like a serious question, has anybody ever cut a brain? Like you did a dissection in high school? Yeah, right? Was that a sheep brain by chance? Yeah, that's typically what. Oh, it was a pig brain. That's something. Either way, it probably had a little bit of the dura on there. If there was like a really tough sort of outer covering on that, right? That would be the dura mater. They don't always remove all of that when they give it to you. The next layer down is the arachnoid membrane, and then finally you have the pia. The interesting thing about the pia is, so your brain, the outside of your brain sort of looks like this, right? It's kind of wrinkled. We'll talk about that. The dura mater and the arachnoid are kind of going to go this way. The pia actually adheres to the surface of your brain, so it goes in and out of all of those little dips and bumps, right? Which have names. They have a general name, so any kind of dip is known as a sulcus. Or if you have 2, it's sulci. And the kind of hills are known as a gyrus, or again, if you have 2 of those, it's gyri. Not only do they have that general name, which I sort of expect you to know, they actually have specific names, right? So there are very complicated specific names for each sulcus and gyrus, which I do not expect you to know. So you can kind of relax on that. Who loves cerebrospinal fluid? Most of you should. Hopefully you have some. Very similar to blood plasma. It's going to be in your ventricular system. We'll talk more about that later. You've got the subarachnoid space. It's a little bit of space between the arachnoid and the pia. It's going to be filled with CSF. You have 4 ventricles. You've got your lateral ventricles times 2, so you've got 1 on either side. Right? They kind of come up. They're kind of horn-shaped. And then you have your 3rd ventricle. There's a little connector between that, and then you get the 4th ventricle as well. Occasionally, your ventricles will get blocked, and that's called obstructive hydrocephalus. Hydro meaning water, cephalus meaning brain. How many of you have heard of like encephalitis? Yeah, it's like brain inflammation, right? I would avoid that if I were you. It's not usually conducive to your normal day-to-day activities. But obstructive hydrocephalus, this happens sometimes in kids. How do you fix this? You put in a brain valve, right? Sounds like a pretty straightforward approach. So you've got your ventricles here. These are your lateral ventricles. They've got those cool horns there, which are awesome. If you look down from the top, that's this guy. You can see the way the ventricles wrap around your lateral ventricles. Your third ventricle's in between, and then you've got that awesome fourth ventricle behind the cerebral aqueduct. Eventually that's going to shoot down your spinal cord. You're going to have a tube running down your spinal cord full of cerebrospinal fluid as well. Here's that kid that had his ventricles all blocked up somewhere. Simply put in the valve, you drain the valve down into the abdominal cavity. The CSF gets absorbed in your abdominal cavity, same as any other fluid, and you're good to go. But you do have this cool brain valve. Do we want to think about development of the nervous system? Well, that's sort of important. So if there's a chance that you're going to be pregnant, you should really not drink arsenic or other things that might harm the development of a nervous system, right? I think one of the obvious ones that we think about now is alcohol, right? How many of you have ever heard of fetal alcohol syndrome? It's a pretty common thing to hear of, right? So to avoid that, if there's a chance you're going to get pregnant, don't drink. That's just, I know that sounds really obvious, but a lot of folks don't think of that, right? Do you know how you know if you might get pregnant? Is everybody aware of how that works? How to prevent that from happening? So, hey Taylor, you want to hear a fun story? And it's about pregnancy. The state of Arkansas has the highest rate of teen births in the United States, right? So what's really, you're going to write this down. What's interesting, you're thinking that's like 13 to 17-year-olds, right? Like the first thing you think of are like kids in high school having babies, right? And so that's not really the case. It's actually like 18 and 19-year-olds who are having babies, right? So that's like really where the peak is, right? So which is one reason you should like get data before you make a decision. So anybody from Arkansas? Anybody ever been to Arkansas? Can anybody spell Arkansas? Just like trying to, there we go, there's a hand, thanks Sean. You're thinking about it. There is not a W in it anywhere, just to give you a heads up. One of my friends from graduate school, not from the United States, he referred to it as Arkansas. Yeah, which it's a great trick for learning to spell it, but you don't sound like you know what you're talking about in terms of geography if you say it that way. Arkansas requires all students who go to a public college or university to take a class about how not to get pregnant. True story. They make everybody take this class. I think it's a short lecture. It's like, here's one thing you can do, just don't do that. I think there's more to it than that, right? Like, here are the things you can do, but here are like 5 or 6 other things you probably should be doing at the same time, right? Because you're not gonna stop activity A. So what are like activities B through D you can do so you don't end up pregnant? Right? So think about that. So development of the nervous system. We'll talk about some developmental disorders later. Basically what I want you to think about is your nervous system really is just a hollow tube. Starts out as a hollow tube, it ends up as a hollow tube. Who remembers those ventricles that we talked about like 2 minutes ago? And I said there was still a tube, right, going down, Rebecca, through your spinal cord, so you still have that hollow tube structure. There are things that thicken and elongate, so you get pockets, folds, whatever. You end up with a brain and a spinal cord. Starts out looking like this. I don't know what that is. Some people will spend a long time on this. I'm not going to. Here's what your brain looks like before you pop out of a uterus. Here's what it looks like sometime after you get out of the uterus. That's what you need to know, right? You're still doing some brain development even here, and it continues for some time. We've color-coded areas for you, right? So you know, like, wow, this part that's green called the hindbrain, guess what it ends up being? Well, the hindbrain. I don't know that that gives you a lot of information or really helps you a lot unless you are a developmental biologist, right, and you're trying to really think about these things. For your purposes, it's not so important. So we can skip that. I think there are people who would spend a long time, right, getting you to think about the telencephalon or the diencephalon, right? And they'll really like pound that into you, right, Jacob? There are people who do this. I think those people are wasting your time. Because I don't hear a lot of people going around and going, wow, that guy's got a messed up diencephalon. That's like taking your car into the mechanic and he comes back out and he says, car doesn't run right. It's not giving you a lot of information, right? There's a lot of stuff in the diencephalon, the thalamus and the hypothalamus in particular. Now we're getting a little bit more specific there, but even the thalamus and the hypothalamus each are probably somewhere between 5 and 30 individual brain regions, right? Inside of that. So even if I say your thalamus doesn't work right, that's kind of saying your engine doesn't work right. Okay, well at least I know it's this giant part, but you know, it could be all kinds of things, right? Maybe I've got a problem with my valves or there's something wrong with the pistons, my spark plugs are bad. I don't know, right? It's not really giving you any more information at that point. So I'm not going to expect you to memorize like some of these major divisions. I don't think that really helps you much. We will talk about specific structures and substructures when we need to. All right, cortex, it develops. Eventually you're going to end up with this 6 sort of layered structure. Your cortex is that wrinkly outer part of the brain. That's where all your fancy thinking goes on, right? This is the part that makes you different from a lizard. Seriously, a lizard brain looks like this. There's a little cerebellum and a brain stem, and they probably have some like olfactory bulbs up there too, right? There's a lizard brain. Here's a human brain. So I'm going to add the part on. I mean, we've got all that stuff too, right? We've got things that help us move. We've got things that help us smell, controls when we're hungry, when we're not hungry, all of that. But we added this big old wrinkly piece on top of that, right? That helps us do all the planning, the problem solving, the tool use. Remember those things we talked about: language, color vision, walking upright, all of that great stuff that we needed for that we needed a big brain for. That's what's going on out there in the cortex. So this guy develops. It's got 6 layers. That's a bit of a lie. Somebody said like 200 years ago it's got 6 layers, Sean, and we don't want to argue with people who are dead, right? Because it's hard to win those. Later somebody said, hey, what about that layer 4? It's got like 2 layers. And somebody said, well, it's got 7 layers now. And they said, well, that's bad because we've already told everybody for like 150 years it's got 6 layers. We don't really want to change our story. So instead they started making sub-layers. So there's like layer 4A, layer 4B, and we realized like even layer 4A has sub-layers. So then it gets, there's like 4A alpha, right? And it gets really confusing. If you know there are 6 layers, I'm going to be happy. Okay? So keep that in mind. Questions about that? Who's ready for a Mythbuster break? We're not going to watch Mythbusters. I'm going to bust a myth. How many of you have ever heard, because I asked my class this the other day, how many of you have ever heard like every time you learn something you get a new brain wrinkle? Don't raise your hand if that's what you believe, but just if you've heard it. Because it's wrinkle, right? Like your brain gets a new wrinkle. Some people have heard that, right?
I was really young, and I was like, how many wrinkles can you get?
Yeah. Like 50.
Oh, plenty.
Not like
It's just, you got to be specific.
she made my she made it better. She said it better.
Yeah. So your brain, once your brain develops, you've got as many sulci and gyri, because we know the fancy words now, right? As you're going to get. Now you can make changes in these cells, right? They'll grow, dendrites or not or whatever. But we're not actually changing that, what we call gross morphology of your brain, right? It shrinks a little bit as you get older. That's mostly because you're losing lipids. There is some cellular degeneration, but a lot of the brain mass that you lose as you get older is really just due to loss of lipids. Nothing to worry about. Your brain shrinks a little bit when you're pregnant too, right? Just to give you a little heads up there. That's like a fluid issue because you're like shooting fluids somewhere else, right, into your uterus when you're pregnant. So you've got like other fluids and things going there, so your brain kind of shrinks just a little. Doesn't affect your function, just slightly smaller. Cortex, we talked about that. Hey, what about progenitor cells? These are kind of awesome. Who loves stem cells? Great answer. I mean, without stem cells, guess where you are? You're not. That's the correct answer. Because we all started out as like half of stem cells, like, right? So you all started out as like two halves of one cell. So that's fun to think about where those came from. And then they slammed together somewhere and started making copies of themselves. It was like, that's awesome. And so you went from like two halves. That's like two halves, right? So that equals one cell. And then it kind of doubles to 2, and then 4, and then 8, and then like 6. That's how this works, right? And then you just make a bunch of divisions, and the next thing you know, you've got Chuck, or whatever you've named your kid, right, after it comes out. In these early stages, though, your cells can do just about anything they want, right? They're young and full of promise and whatever. They've not decided they want to be a liver or a brain or an earlobe yet, right? I mean, think about those cells that really just want to be earlobes. Earlobes are important, right? So, early on, you just have these progenitor cells. They're stem cells. Now, as an adult, there are a couple places where you have stem cells still, as far as we know, all the way until you die. Some of those, you think about your hippocampus. We'll talk about that later. There's no genesis going on there. Also, your olfactory epithelium. So that's kind of like you can get to it with a pair of needle nose pliers, like going straight up your nose. That's a true story. So they can harvest stem cells from your olfactory epithelium that way. Those kind of go up in your nasal cavity and pluck things out. Yeah, I mean, I wouldn't try it at home. I mean, you have to sterilize your pliers first. So there you go. They don't do you a lot of good there. They just help you make like new olfactory cells, which are okay because your olfactory cells die. We'll talk about that later. Complex brains, we like those. Don't have to think about this. We do have some kind of longer period of divisions, right? If you want a bigger brain, then you need to spend more time building that, right? I mean, that just makes sense. It's not a real surprise. Now, there is something interesting here. We'll talk about overproduction and refinement. The word that we typically use is synaptic pruning. How many of you are pomologists? No one's going to answer that. No one knows what a pomologist is. It's people who like study fruit. That's just a side story. Anybody like pomological art? Like you ever see like those pictures of art or of like fruit that's been sliced in half, right? And you can see it. The reason they did that was a copyright issue because there were people like developing all these like fancy apple types a number of years ago, and they wanted to make sure like they were getting credit for their new fancy apple, and so they would pay they would commission an artist to come in and paint, do an image of their apple, so that they could, when they found somebody else like selling their apple, and they weren't authorized to do so, they could say, "That's my apple. I paid this guy to paint a picture of it." Like some court documents. It's a true story. So we need to do some synaptic pruning. You're born, and then you spend a few years like just continuing to develop and add connections in your brain, right? You're going to add synapses, you're going to add dendrites, axons, all kinds of stuff, right? You've got this early period of this overproduction, right? So we're going to produce more of these connections than you actually need. As you start to get a bit older, we're going to go through this pruning process. We're going to trim away the things that you don't need, right? So we're going to cut away the connections you're not using, the dendrites, the axons, the things that you don't need. We'll prune those, we'll get rid of those, right? You might think, why would we make more and then get rid of that? Seems wasteful. It is a little bit, but it's easier than trying to add in all of the connections later, right? Because that's like trying to find your way through a bowl of spaghetti, okay? Because you have like a trillion neurons, and those trillion neurons have some untold number of dendrites, right, coming out of them, and so you've got to try to navigate these connections. It's much easier to overproduce, and then as we need to, cut these guys out that you're not using, right? And so what you'll end up with is something that's much more functional, right? This is why if you like, I don't know, you might want to try this sometime, like poke babies with a stick, right? It's just like randomly. I always walk around with a stick, in case there's a baby. You never know when you need to, like, you know, shoo that away from you. So if you poke them like in the arm, and then like their leg starts moving, right? They're not really well connected. I mean, they're just random balls of flesh and brain connections, right? So that maybe, like for those of you who have kids, I should have told you this decades ago, and so your kids would make more sense to you and have a little patience with them. I remind my mother of this, right? Like when she gets frustrated for something I did before, I'm like, look, it wasn't my fault. I had no idea what I was doing. So, yeah, Sean?
Does that have anything to do with like why it's easier to learn a language at a younger age?
Sure. You know, and that's a big debate you're going to get into with like developmental folks, like critical periods and all this stuff, right? About when is the ideal time to learn things. It's much easier to learn when you're younger for a lot of reasons, right? One, related to this, you've not chopped away those connections you're not using. You might decide you actually want to use some of those, right? And you can retain different ones, right? You're not necessarily going to retain more. I mean, you might, but I wouldn't think about like trying to learn an extra language so you retain more of these connections. You're just going to cut out other things. It's not going to be a significant difference, right? But two, the younger you are, you know, this may come as a shock to you. The younger you are, the better stuff works, right? The older you get, the less, you know, things don't work as well. And that's not just like your knees and your hips. That's the other parts as well, including your brain, right? And some of your metabolic things slow down. You still have neurogenesis going on as an adult, but it's like restricted to two regions, right? We're not talking about sort of a broad global thing when we have to have that extra energy if we want to sprout new dendritic spines or something. That's going to be easier to do at a younger age, right? And so you've got that mechanism as well. So you've got more connections that you can take advantage of, but you're also, if you need to make some adjustments metabolically, that's easier for you to do at a younger age. And you're not kicking in sort of any neurodegenerative things. This happens over time. Your cells die all the time. It's not typically a big deal unless you develop a neurodegenerative disorder like Parkinson's disease and start losing a whole bunch of cells in one brain region. Does that make sense? That was a good question, Sean. So, I know some of you have heard of this thing called apoptosis. I really think that P should be silent. I think it's apoptosis, right? For the same reason you don't call it a pterodactyl. So if you think about that a little bit, it makes some sense, right? So, apoptosis. If you hear me talk about that, and you've heard apoptosis from someone, Jacob, is the same thing, okay? Because there is something called ptosis, right? That's like a drooping eyelid. And I don't, you know, because I don't think you call that ptosis, right? It's just ptosis. And I think apo is like, it's a little different, so apoptosis. Anybody heard it that way with the silent P? No. Yeah, you're only going to get that from me. And like the guy who taught me, who was obviously knew what he was doing. Pterodactyl. I also randomly want to yell out Socrates for some reason, but like two people are going to find that funny. I thought it might be the two of you for some reason. Really? Wow. There you go. You should all go home and watch Bill and Ted's Excellent Adventure. Probably Keanu Reeves' best movie. It was better than Speed or Chain Reaction. Any of them. What were the other movies he was in? I don't even know any other ones. It's not his fault. He's got the Kit Harington disease. He's got one tone of voice and one look. It's the same. Sorry, didn't mean to like crash Kit Harington for you there. If anybody was a Kit Harington fan, anybody? No takers. It's Jon Snow from Game of Thrones. It's not ringing any bells. Great. Did you watch that Gunpowder show that he was in? Yeah, about Guy Fawkes. I thought he was going to be Guy Fawkes, but he wasn't. Because I thought, if I'm going to put Kit Harington in a movie, I'll just put a mask on him. Right? Because it's the same face all the time.
The girl from Twilight. That's the one. She has that same look.
Yeah.
Same tone of voice, everything she does.
Creepy. There are a lot of creepy people out there. If you're trying to cast a creepy people movie, I can tell you a couple roads to go down in town. Lots of folks you could hire for that. So, don't worry about this. Forebrain. Hey, this is when I'm saying like forebrain. Okay, so let's think about the forebrain for a moment. This is important because there are different parts that of your visual or of your sensory cortex. We'll talk about that later. So this guy in this beautiful teal color is your telencephalon. All right, Caroline, you've got this, right? Telencephalon. What are you going to do with that? Do you know what? Do you know? I mean, what I think is important about this is like this little bit of your telencephalon does something, and this one does something different, and then like this does something different, right? And there's a different piece here. This guy is doing something different, and this little bit here, and then what does it matter to you that you know the whole thing's called the telencephalon, right? I mean, I think this misleads you into thinking that this is all homogeneous, right? And it's all doing the same thing, Kata, and it's not. It's all completely different brain regions. They all have their own specific jobs. Who taught us that? Who remembers Pierre Florenz, right? And the brain spoon, right? We learn that, you know, you remove different parts of the brain and you lose different functions. I guess I should put Paul Broca there too. Right? And I should also really give the credit to Tam, because he's the guy that actually had the brain injury. So all of these little pieces are different, right? And they're different areas. And there was a guy later, his name was Brodmann. You don't need to know this, but I'm going to write it down anyway. Brodmann came in and said, hey, I know they're all different areas, so let's give them all numbers. And now there are things called Brodmann numbers, right? And so there are like, I don't know, 100 different areas or something in the cortex that are different Brodmann's areas. So people have realized, like the forebrain, whatever, it's bigger in mammals than it is in other, like, families. It's bigger in humans, more complex in humans, I should say, than it is in other species. Here's your diencephalon. That's going to be the thalamus. And then down here is your hypothalamus. Hypo means below, right? So it's below the thalamus. Not a big deal. This guy's your pituitary gland, that little punching bag. This is an important one. We'll talk a lot about the pituitary gland later in this semester. That's responsible for hormones. Who loves hormones? Nobody wants to answer. Like, the correct answer is yes, you do, right? You love hormones because that's what allowed you to grow and develop, and that fun thing called puberty happened to you. Most of you, just looking around, you can kind of tell if somebody's been through it or not, right? If you haven't, just hang in there. It's coming. Some of you are like nodding your heads like, yeah, I'm just waiting on that, right? Like you're not sure if you made it through puberty or not. I don't know, I'm trying to think, like, what's the safe way I can tell them to check? Like rub their armpits, I think, right? If your armpits smell and there's hair there, or it does grow hair, like you have to remove it, then you've been through puberty. There are a couple other places you can check too, but I probably shouldn't tell you to grab those in class. I think I could tell you to put your hand in your armpit. For a few of you, I could say rub your face, and that would work. But that does, it applies to Sean, but doesn't apply to, maybe Taylor, for example.
Well, yeah, when the hormones go away.
That's menopause. That's a whole different, that's a different story there. We'll talk about that as well. When your ovaries decide to retire, and all you're left with for hormones are coming out of your adrenal glands. Yeah, we'll talk about that probably after the midterm. Hey, who remembers the sulcus and the gyrus story? Guess what happens if you get a really big sulcus? We call it a fissure. Nothing fancy. You really only have a couple fissures. You've got one here and one up here. The rest are going to be sulci. I'm not going to expect you to know that. Hey, what about lobes? You guys know the lobes, right? The frontal lobe, the temporal lobe, occipital lobe, and the parietal lobe, right? That's a little bit better than just saying it's all telencephalon, but it's not a lot better, right? So I'm not going to spend much time on that. Now here we've labeled different parts of cortex. This is kind of interesting. We'll talk about these areas of cortex. For example, we'll talk about primary visual cortex when we talk about vision. That's obvious. We'll cover the motor cortex, somatosensory cortex. We'll talk about movement and body senses, auditory cortex. We'll talk about frontal and prefrontal cortex when we talk about things like schizophrenia, when we talk about learning and memory, higher order functions, things of that nature. So right now you don't really need to spend a lot of time on it. It is highly organized, right, which is really interesting. And for most folks, you can go in and sort of remove, specific places. Like if you cut that part of the brain out, somebody's not going to be able to move in that case, it's going to be their right foot because it's the left hemisphere. Remember that decussation where things cross over. So you have, left to right, right to left. Seems reasonable. I think it's the other way around, but you got it. Lobes, let's skip that. Corpus callosum, we talked about that. We don't really need to spend much time on this. Well, I guess this is kind of interesting. We should think about motor control. How many of you have ever moved? Just your body in general. I know all of you have because I'm in this room on Tuesday. I didn't see any of you. So I'm assuming you get up and you move around. It's a very complicated thing to do. So Jacob, you're going to think about leaving here at some point. Right? You're probably thinking about it now. That's fine. But definitely you're going to think about it when class is over 4 hours from now. So you're going to get up and you're going to walk down, and I don't know what you're going to do once you get out of that door, and I don't really care. That's a lot of planning, actually, right? You don't think about it. It's a very simple task. But there's a bunch of your brain devoted to telling your body to move, planning how your body is going to move, navigating your environment, right? How many of you love robots? I'm holding out for a robot that's just going to do everything for me. So that's going to be exciting. One of the reasons we don't really have like human-like robots right now is it's been very challenging to create a robot that can walk. Okay? Walking is one of the most complicated things that a human will ever do, right? Walking. And if you don't believe me, really for a moment think about what you do while you walk across campus, right? Campus, the surface of campus is sort of like this, right? Wait, there's a pothole. And then right about here's a squirrel that's going to attack you from a trash can. So it's on top of the trash can, straw its little tail, and then its rabbit teeth. Right? There are all kinds of things that you have to avoid. And then the other thing, like here's that professor for whom you still have homework out and you don't want to see her. So you're going to try to dodge her and you're going to take a different path as well. Right? Sydney, these are all things you're doing while you're walking, right? And you're just like walking along and you think, how easily do you adjust to these changes in terrain? It happens all the time, right? You don't even think about it. You don't think you think about it, right? Because it's not in this conscious awareness, but like all of this part of your brain is really working on that. Right? It's really solving those problems for you. How many of you play sports or have played a sport? Okay. Anybody curling? It's a good one, right? I think like I should have done that. I think if I have kids, which I'm not planning on, but sometimes they just like show up at your house. And if this happens, I'm going to train them for curling. And the reason for this is that, A, I don't think there are a lot of people getting into curling, right? And so I think, well, that's like a path to success. But 2, it's the same motions for cleaning my floor. And so it's a 2-for-1 right there. So I get clean floors and I might have a kid that's an Olympic athlete. So if any of you are going to have kids, consider that. The other thing, this is a true story. You should read this book called Outliers. Just you, Jacob. It's really interesting. Like, the overwhelming majority of hockey players in the NHL are born between like January and March. The overwhelming number of like Major League Baseball players are born like August. Yeah, like they're in the summer. The reason is the cutoff dates for when your kids play sports, right? So if your kid turns like 10 on January 1st, they're going to be playing against kids who didn't turn 10 until December 31st. So they're going to be like a whole year older, right, than this kid down here who's going to be 9 like the rest of that year. And that's a big difference when you're 9 and 10. Not such a big difference when you're like 35, but at 9 and 10 it is. So that's something to think about too. So if you have kids accidentally, because I'm going to recommend you don't, think about when you have them, and then think about what sport is appropriate for them, right? What's the cutoff date? So they're going to be the oldest kid playing that sport when they're growing up during those formative years. It's going to help you out. So, walking, complicated, constantly doing these things.
Well, let me ask
I don't even think
you
about it.
Those things are, you do them without thinking about them.
Yeah.
What if you have to think about them to do?
It's going to slow you down.
Walk?
It's going to slow you down.
Is there any way to make it better or make it? Can you do anything to your
So,
brain?
if you're thinking about someone who's had, you were thinking about a stroke, we're thinking about neurodegenerative disorders, we're thinking about something like that. Unfortunately, with central nervous system, recovery is minimal, right? And there are a number of folks who've had severe injuries to different parts of their brain, and they have to think a lot consciously about what they're doing. There are cases where folks, if they pick up something, like most of us can like pick up something, we can walk like this, right? It's not a big deal. You know you got something in your hand. There are some people who have to continually look at what they have in their hand, or they'll not realize it's there and they'll just drop it because they've had some damage to particular brain circuits. So, unfortunately, at this point, there's not a lot of. You might see a little bit of recovery early on as like brain inflammation goes down and blood supply returns, but that's going to plateau pretty quickly. I know it's not a real uplifting story. The less uplifting story is, in all honesty, I don't think there's going to be anything we'll do about it. And the reason for that is you're going to have to figure out, see, I'm going to draw this cell right here. You're going to have to figure out how that particular cell is connected to this particular cell and like all of those 10,000 connections in between. And that's going to be a really hard sort of piece of thread to weave in there, right? And I think that's a problem. You could try to bridge that with some electrical stimulation, but that's going to be really broad, and you're going to be activating a whole bunch of cells and then a whole bunch of cells down here, and I don't know that that's going to, if there's a complete disconnection between those two brain regions, then maybe that works, because then you can have at least some connection, but it's not great. It's kind of a similar story with cochlear implants. You might know folks who have cochlear implants. It's sort of an electronic bypass of the cochlea, which works not quite as well as an actual cochlea, right? So they'll like collect that sound, convert that into an electrical signal, zap it into their auditory nerve, and then on into the auditory cortex. But what they hear is not of the same quality as what someone who doesn't have cochlear implants hears. For that reason, we've not quite mapped all this out so we can have electronic prosthetics. Don't worry too much about this. This is diffusion tensor imaging. We'll talk about it if we need to. Here's a guy whose brain was cut in half. All right, let's talk about some specific brain regions, right? Because we should do that. Again, broad overview here, Sammy, so I don't want you to like really dig in. Are you wearing a Michigan hat? Yeah. I just realized, for a moment I thought it was either old or I'm colorblind. But I'm not either of, I mean, I don't think his hat's old and I'm not colorblind. Oh, sure, whatever.
Look for the quizzes after the weekend.
You're going to do the quizzes now.
Right now. But it'll take me until the end of the weekend. Working steadily.
Shouldn't you have to wear like a Marshall hat? I mean, you're just like trying to fake us all back there? Or is Marshall trying to rip off Michigan? Because it looks like the same M, right? I guess there are only so many ways you can make an M. Alright, that's a good story. You know, there's like a whole group of people on this campus who tell me what color I can send out a picture of the Marshall M. You know what I think about that? I'm going to go on the record. I think it's a waste of money. You know where that money could have gone? My pocket.
There's actually like an organization that takes care of that too. One of the high schools that was our school rival, their W matched Wisconsin and they got sued for it and changed their W.
Yeah. There's even that same group that won't let me send out like non-Kelly green Marshall stuff. Also tells me what font to use for my emails. Like there are certain fonts they don't want us to use. Whenever I send that group an email, I put it in Wingdings. Let them decode that one. Actually, I've never sent them an email, but I have that ready just in case. I know it's going in Wingdings because that's the way I do it. All right, let's talk about the limbic system briefly. This guy's going to be involved in emotions, a few other things. The big guys we want to think about here, there are some cortical regions, but we also want to think about the hippocampus. We're going to talk about the hippocampus a lot when we talk about learning and memory. And the amygdala, which is the like fear nucleus, right? So we'll think about it with fear, anxiety. We'll talk about those. Obviously, fear and learning and memory, those things are connected, so we'll kind of draw the circle there when we get that far, so that'll be exciting. You don't have to worry about these other regions. There's your amygdala. It's from the Latin word or the Greek word for almond. How many of you love almonds? Yeah, there you go. Thanks. Almonds, you know, nature's energy source. I don't know. I don't really have a pitch for almonds. But the amygdala is sort of almond-shaped. The hippocampus here, so like here's one side of it and there's the other side of it. That's seahorse, right? So it's kind of shaped like people think it looks like a seahorse. I don't know. I know, right? That's the face I made. I was like, seahorse, really? I don't know. But what you have to realize is a couple things. One, the people who were doing these like early brain dissections, they were like just huffing these chemicals all day long, right? These like fixatives and formaldehydes and things. It's like, I think they were like, you know, their eyes may not have like focused on the same thing there all the time, and they were just crudely cutting things, right? And so when you were to get something out, and you're like, well, that looks like a seahorse there. Let's go with that. So some of those things might be a little different than what you would imagine. Hey, who loves the basal ganglia? These guys are fun, right? There are a bunch of structures in the basal ganglia. Some people will give you different answers. Mostly we're going to think about the caudate and the putamen. Globus pallidus is going to be in there as well. A few other places, nothing to worry about. These guys are involved in motor movement, right? So motor movement. When you have Parkinson's disease, there are some structures in the basal ganglia that are damaged, right? They're degenerating. Same thing for Huntington's disease, although they're sort of opposite diseases. We'll think about that when we get there. Other disorders that have motor components to them are going to implicate the basal ganglia. Some that you don't think about quite often are autism, right? So if you think about individuals that have been diagnosed with autism, quite often they have a repetitive stereotyped behavior, right? So they will often kind of rock back and forth, or they'll make the same movements. Other Tourette's, right? So you kind of have those uncontrollable tics, right? So that's going to be something that obviously is going to involve some motor movement. Basal ganglia is going to be there. And then OCD, obsessive compulsive disorder, right? Not so much the obsessions, but the compulsions, right? You think like, oh man, germs are going to kill me. Well, which they might. But it's the hand washing, right? So it's that continual ritualized movement, right? If you think like my gas stove is going to burn down my house, so I'm going to go turn off the knobs. You know, there are people who like turn off the knobs like 50 times, right? So it's that continuous repetitive motion. We'll talk more about that later, but let's just give you a little heads up. In that great, wonderful diencephalon, you've got this guy called the thalamus. Primarily, this is going to involve sensory information, right? Information that's coming from the outside world is going to stop off in the thalamus for a little bit of processing before we send it on up to cortex to do other things with that, right? So we're going to do a little extra processing step there. Hypothalamus, again, it's going to have some hormonal control. It's going to tell your pituitary gland to release hormones that will tell other places to release hormones. It's kind of like a three-step process. We'll talk about that when we get there so that you have that you have that foundation. Hypothalamus is also involved in things like circadian rhythms. Right? How many of you have ever tried to sleep during the day when the sun is shining in your face? Doesn't always work, right? That's why I have an eye mask. And I have a blind on the window in my office, so I just pull that down. Take a nap in there. That's because when the sun hits your body, it activates something in the, we'll talk about it, the hypothalamus. The hypothalamus says you should probably be awake, so it'll release like some stress hormones to get you up and moving, right? How many of you love cortisol? It works, right? There's actually a little bit of a peak in cortisol levels early in the morning, and that's it's a stress hormone, but it's to get you up and moving, right? Because it kind of activates that sympathetic nervous system. So get you up, get you moving, until you can like get some coffee or cocaine, whatever it is you need to get you through the day. There's your basal ganglia, these fun blue guys, and these two whatevers are the thalamus, and your hypothalamus is tucked in under there. Hypothalamus, again, it's small but important, and I'm going to put important structures, right, because again it's multiple nuclei. Really important for survival and the things we call the 4 F's: fighting, fleeing, feeding, and reproducing. Questions, comments, concerns? We're moving right along here. Not too much to worry about here. There's your thalamus, pituitary gland, hypothalamus is here. Later we'll talk about optic chiasm, but you don't need that right now. Tectum, tegmentum, I'm not going to expect you to know too much about that, although the tectum has a thing called the superior colliculus. Colliculus means little hill, right? We'll talk about this guy when we talk about the integration of vision and motor systems. How many of you have ever heard a noise behind you and turned around to look at it? It happens, right? All the time. It should happen. If not, sometimes you'll get kicked, because the noise behind you was someone coming to kick you. So you have to really turn your head and take a look. Your superior colliculus is going to integrate that information. There you go. Colliculi is plural for colliculus. You've got one on the left and one on the right. Inferior is going to be more auditory stuff. The only nucleus here that I think is important is the, it was an interesting noise, is the substantia nigra. This guy projects to the striatum. If you have Parkinson's disease, the dopaminergic cells in this pathway die, and that's what gives you the motor deficits, right? That's why we'll call this the nigrostriatal pathway. We'll talk again more about that toward the end of the semester. Right. We should talk about the hindbrain. Hindbrain's got basically 3 areas: the cerebellum, the pons, and the medulla oblongata. What do I want you to know about this? The cerebellum is important for coordinated movement. How many of you have ever been walking along and you kind of stepped through the floor, but you caught yourself before you went all the way down the stairs? Right? You have anticipated some sort of motor feedback. You didn't get that, and so you stopped, and it felt weird, right? You thought, something should have happened there. And so your cerebellum is the one that's predicting that, whatever that is. When that doesn't happen, your cerebellum will sort of sound some alarms. It's also one of the first guys to be affected by alcohol. This is why there's an inverse relationship between what you think your physical prowess is and what it actually is when you drink, right? So the more alcohol you ingest, you definitely think you can jump that, but in fact you can't, right? You probably never could, but you definitely can now. So it doesn't make you, doesn't make you better, it makes you worse. So keep that in mind. Other things in the hindbrain, down here in the brain stem, I call these guys the idiot box, right? These are the things, if you had to think about them, you would die. Like breathing, your heart pumping, blood pressure regulation. There's some other things like pupillary reflexes, stuff like that. It's back there in the brain stem. And if I gave that job to you consciously, I'd be speaking to an empty room, right? because I know, like, how many of you have forgotten something before? How many of you just realize now you forgot something that you should have done, and you really just want to leave and go take care of it? Right? Nobody's going to own up to that. That's great. Obviously, Jacob had something that he forgot to do, so he forgot to put up your quizzes. So that stuff's going on in the brainstem. No worries there. Here's your brain. Hey, how do you know when you get out of the brainstem and you end up in the spinal cord? There's a sign. It looks like this, and it says spinal cord 500 millimeters. No, that looks like a road sign, right? That's not going on. Once you get out of the brainstem, you lose some of these other nuclei, and you end up with just spinal cord. What's important about the spinal cord? I think about this like an elevator, right? Some information's going up and some information's coming down. Unlike an elevator, like in this building, when the elevator goes up and down, right? It can go both directions. You have to get on the path going up or the path going down, right? So maybe it's more like an escalator. But for that, you'd have to really just like lean over at a 45-degree angle. Information that is in sections that are in blue are what we call ascending tracks. And they're going to be on the ventral. Ventral is sort of the anterior side, right? So the side facing to the front. The red tracks are going to be descending tracks, so these are motor commands going down, so they're going to be on the kind of running down the very back of the spinal cord. Okay. The size and shape of these ventral and dorsal tracks, these ascending and descending tracks, are going to change as you go up and down the spinal cord, right? Because you're going to be collecting more information or sending, you know, as you go down. The farther down you go, the smaller the descending tracks can be, because some of those connections have jumped off, right? Once you get past like your arms, for example, you've lost some of those fibers, right? But you have more as you're going up on the ascending side. I'm not going to ask you a whole lot about that. Hey, you've got cranial nerves. These are nerves attached to your brain, right? They come off the bottom of the brain for the most part. They've got sensory and motor functions. Mostly, they're going to be related to things in the head and neck region. There's one exception to that, and that's going to be the vagus nerve. That does not go to slot machines, just in case you were curious. It's the other kind of vagus with an A. That is from the same root word as vagrant. Don't answer this, but how many of you have been vagrant? How many of you have wandered the streets without money? That's what it means to be vagrant, right? Just to wander about with empty pockets. I think that describes most college students, right? You're just wandering about. You don't really know where you're supposed to be at any given moment. And I know you don't have money, right? Because you spend it all on Scarface posters. Is that still a thing? Do you guys still buy Scarface posters? No? No, that's not now. You still buy like Animal House posters with college on the sweatshirt? You're not sure you ever did? What are you guys doing? It's like the stereotypical college posters, right? I mean, they still have poster cells on campus. I mean, why do they think college kids want posters? I don't know, right? I mean, like, I don't know. Anybody? No, nobody's going to answer this. Who visited the cannabis the other day? And you have to pronounce it cannabis because it actually is a bus. It's not cannabis. I mean, they were selling cannabis-related things, but they were in the cannabis. Yeah, it was parked down by that abandoned church on Fifth Avenue, right? You know, there's that church right kind of over there where the indoor practice facility is and the stadium parking. There's like that. I think it's a church, right? I don't know.
It was right across from Subway.
Yeah, right over there, right?
Next door to
This
Subway.
giant old school bus, and they had cannabis written on the top and like marijuana flags. Nobody went there. Huh? Yeah, I don't know that it was advertised. I don't think there was like an MU announcement about that. I don't think, you know. I'm not going to speak for someone's personal views. I just don't feel like as like, you know, the president of a university, someone should send out like, hey guys, the cannabis is down the street. I don't think that's coming out, but, you know, I don't know. So nobody went? Someone went because someone's still laughing about
No, I didn't go.
it. You sure?
I didn't go. I just saw it.
Yeah. I drove by and I was like, what's that broken down school bus over there doing? And then I was like, oh, it's got a bunch of flags. I heard he had a dog. So some people went by to pet the dog, is what they told me. I don't know. Somatic nervous system, whatever, that's your body. Autonomic nervous system, we talked a little bit about that. You've got two divisions of your autonomic nervous system. The sympathetic is the one that gets you revved up, and the parasympathetic is the one that brings you back down. That's pretty straightforward, right? Hey, there are your cranial nerves. You've got 12 pairs of these. I love this one that goes right up the guy's nose. That's my favorite. But they go a variety of places. Again, that vagus nerve being the sort of exclusion, and it sort of goes everywhere. Spinal cord, don't worry about that too much. And that's the end of chapter 3. See, I told you that was going to be straightforward and easy. Any questions about that?